So, welcome back to the lecture series on bioenergy. So, in the last class we talked about the combustion process. So, now we are in the fragment of different conversion strategies from biomass to energy, and in the combustion we ended up with how heat energy being used to generate electricity by generating sufficient amount of steam from water by boiling the water, and that steam is fed to the generator, and that is how the electricity is being produced. Okay. So, today what we will do in that series, let us coming back to the chart where we were. So, we will be touching upon the process of pyrolysis. So, as compared to combustion where we are using in the presence of oxygen, here it will be in the absence of oxygen. Okay. So, as we do in every class, before we really get to the details of the process, let us try to understand the whole process. If you break this word pyrolysis into two parts, pyro plus lysis. Pyro means fire and lysis means you are breaking down something. So, in other words, you are breaking down something in the presence of fire or heat. You can also call it a thermolysis. So, say for example, if you have a material like this which consists of carbon, hydrogen, carbon, nitrogen, sulfur, whatever, you can keep on adding all the different kind of elements. Now, you exposed this, you heat this up, you provide heat energy, and you maintain this, you provide the heat energy in the minus oxygen environment or no oxygen. Okay. So, this is the situation. So, you have no oxygen and you are giving heat to any form of biomass around say 350 degree centigrade to 500 degree centigrade. Typically, you can go up, you can all the way go up to 800 or you can go up as much as you can, but typically this is the range. So, think of a situation, you have a material, you are heating it in the absence of oxygen. So, generally whenever we heat something, there are 2-3 things which could happen. Of course, in the presence of oxygen, most of the carbon matter, it becomes carbon dioxide and moves out. And because of heat, sometime the matter transform into change its state. If you are in the solid, it may go to the liquid state, and sometime it may even go to the gaseous state, depending on its at what temperature it changes the phase. Like you have seen naphthalene balls, they directly from solid they transform into gaseous state. Okay. So, you see that naphthalene balls are used inside to protect our woolen clothes and all those kind of stuff. Okay. Similarly, there are materials which from solid phase they goes into liquid phase. Okay. Similarly, there are materials which from the liquid phase moves into the gaseous phase. So, there are always phase transitions which take place in the form of, so from solid to liquid to gas, or even this is not that strict, it could be like this, okay. So, it could be like this, so on and so forth. So, all you need to have this kind of phase transition is some form of energy, either in the form of heat, light or whatever, you know. You just need certain amount of energy by virtue of which you can make this thing happen. So, now if you think of, so you have this organic matter or biomass with you, which is a solid material, organic matter or biomass. Now, what you do is, in the absence of oxygen, no oxygen, you raise the temperature inside a chamber to 500 degrees centigrade. Irreversible change takes place. So, you cannot really go back. Irreversible change occurs in the phase of the matter happens, and this irreversible change leads to generation of multiple products. There is something called pyro gas. Okay. This is the gas which is liberated out. It generates something called pyroliquids. The pyro is the word which is used because this is getting generated through pyrolysis process, which is also called commonly as bio oil, and you can call it even pyrodiesel, but that is kind of, you know, the tricky way to achieve that feat. Then you have solid residues which are present, which are called chars, solid residue, and solid residues are termed as char, or, and since it is coming from charred materials. So, you know, charring has been the word you must have heard, it got charred because of fire or something. So, it is a charred material, and since this charring is happening in a material which is a biological origin, it is also called biochar. Okay. And if you go really extremely, increase the temperature further up, and you go for a very heavy pyrolysis. So, what you would, this is also called an extreme pyrolysis. For a prolonged period of time, what you will get is a carbonized product. Just left behind is the carbonized product, and this process also, this pyrolysis process at times is also called a carbonization process. The name itself is self-explanatory. Carbonization means the formation of carbon, rich carbon residues which are left behind. Okay. So, this is overall what could be done, and if you look at these products like chars or biochars which are present there, or extreme carbonization processes. So, this is not something out of the world. You all have seen one thing, you must have seen after harvesting of the crop in the fields, especially in the northern part of this of our country, you will see the farmers burn the field after harvesting, especially to get rid of. So, when you are, so what happens when you are, like say for example, you see a field, you see that the plants are, or you know, the crop is growing like this, okay, in the soil. Okay. Now, when the farmer cuts the crop, they cut it like this, okay, cut it here. So, still what is left behind is the part of the residue. Then the farmers burn the field, which takes care of this part of the residue and kind of leaves behind a charred look of the field. this is nothing, this is an incomplete, so of course, there is oxygen present, but it is an incomplete burning. Okay. And these charring is very similar, except the fact this kind of charring happens in the presence of oxygen, but when one can do that kind of charring in the absence of oxygen, you get this kind of things. And because of that incomplete charring, what you get, those kind of biochar stuff, what we get, they are very good for the soil because they are rich in different elements or alkali metals like sodium, potassium, like, okay. And they are also, some of these biochar materials are also used for water filters, because these are very, very porous material, and you must have heard about activated carbon and all these things which are used. So, these are all produced through this. So, if you look at it, if we go back a little bit in the previous slide what we talked about. So, when a charring process or the pyrolysis process is being done, what we get is a pyrogas, which is a form of fuel, and we will talk later, not in this class, in the next class what are the challenges in it. Then we get what is called pyroliquid or bio oil or even pyrodiesel. This is another form of fuel, whereas this solid residue which is left behind has implications or has significance or even carbonized product for soil improvement as well as water filtration. And this biocharring or pyrolysis process is very, very extensively used in the chemical industry, chemical engineering, in order to produce myriad of different kind of products. Okay. So, the process, what is significant here to realize, there is one point which I did not talk. So, I showed you that you are raising the temperature around, from 350 degree centigrade to 500 likewise. Okay. Now, this parameter is controllable. How you are raising the temperature? What does that mean? That means I can raise the temperature like this. Say I start with, say, typically a room temperature of 37 degree or 30 degree, okay, and I switch on the heater. So, before I get into this, just I will give you an idea that how the biocharring apparatus generally happens in a laboratory condition. There are big biochar apparatus. So, it is something like this, okay. That will kind of help you to visualize how the structure looks like. So, the structure looks like this. You will have a box like this, which is kind of the reactor. Okay. So, okay. So, in that box you have a tube coming in from here, which actually runs through like this, comes out. So, there is a tube inside from this wall, like I am just shading the wall for your understanding. From this wall one tube has gone. Okay. Okay. Now, you have a source of inert gas which you purge into the system, and which ensures that this whole tube. So, you can seal the tube from both sides. Okay. Now, say for example, you have a material which you need to pyrolyze. So, I am putting the material like this. Okay. So, you left the material like this. Okay. This is the material for pyrolysis. Okay. And you have the inert gas in the form of argon or nitrogen, you can use as the inert gas. So, you are making this whole chamber free of oxygen. So, this is an anaerobic situation, anaerobic environment. Okay. So, there is no oxygen out here, and around this there is an heating element whose temperature you can control from outside. So, here is the heating element. Okay. So, what you do is you keep the sample, step 1. So, let me put, this is the step 1, you get the material, this is the material you want to biochar or carbonized or pyrolyzed. You seal the chamber from both sides, this is step 2, sealing the chamber. Point 3, you make the whole environment inert, step 3. Then once you are sure that this whole environment is free of oxygen, then you switch on the heating element. Now, this heating element can take the temperature, say, all the way up to 1000 from wherever you are starting, say 30 degree or whatever is the temperature inside it. Now, there are multiple ways you can raise the temperature. You can do it in small step cycles, 30, 40, 50, 60, 70, 80 likewise, okay. And whatever the temperature you set, say for example, you set a temperature that I want to reach 500 degrees centigrade, right. Yet that is called a slow pyrolysis. You are raising the temperature slowly and you set the, once it reach the set temperature, you stop there. But there is another way you can raise the temperature. From 30 to 500 you can reach, like in few seconds, 2 seconds, zoop. Something like, just imagine, say for example, all of a sudden there is a volcanic eruption and there are all the trees which are present there, and the volcano, the lava fall in a fraction of a second. The whole material, the whole vegetation get converted into, charred, millionth of a second. So, exactly similarly like that, similar to that, you can really jack up the temperature like soup. Instead of having the temperature curve like this, say for example, you are the stepwise temperature you are increasing, okay. You are reaching to this point. Say for example, if this is say 50 degree centigrade, this is 500 degree centigrade. Over a period of multiple cycles you do it, over say half an hour you go. Whereas you can actually reach it like this, boom, and say in 2 to 3 seconds, okay. Such processes where you are raising the temperature like soup, like this, is called flash pyrolysis. And it has its implications, I will come. So, what you can control here is how the temperature. So, say for example, flash pyrolysis you can understand or visualize it better if you think of all of a sudden there is a volcanic eruption and the molten magma or the lava falling and covering the vegetation in a fraction of a second, and the whole vegetation, because of that excruciatingly high temperature of the molten magma or the lava, just get carbonized in like this. So, that is a flash photolysis, sorry, flash pyrolysis. Okay. Now, flash pyrolysis has its advantages. So, what is happening? Let us coming back out here, slide, or I will showing you this process. There is an irreversible change which is taking place. I mentioned this, right. This irreversible change is nothing but a phase transition of matter. Okay. Phase transition of matter, and not only there is a phase transition, there is a change in chemical composition. Okay. there is a drastic change in chemical composition. Apart from it, its physical properties also changes drastically or almost irreversibly, changes drastically. Now, this whole thing is a function of how you are raising the temperature. It has been observed that several biomass, when they undergo a flash pyrolysis like this, they get transformed into liquid as well as gaseous fuel very fast without leaving behind much residues. And these are some of the very interesting techniques. And even talking about pyrolysis itself, if we talk about the whole pyrolysis process, if you think of how over the ages, over centuries, over millennia and billion, the coal and all other products have formed, essentially what has happened if you think of it underneath the earth. So, if we talk about through geological times, the trees, so underneath the earth, if this is the earth crust, so over the years all the trees and vegetative matter has gone down, through the ages, and these biological organic matter, in the absence of oxygen, because underneath the ground you will have very little oxygen or almost no oxygen, and you will have higher temperature and you will have a higher pressure. So, under these conditions, several of these things have got transformed over centuries to the products which we are enjoying today in the form of coal, in the form of petrol, in the form of diesel, and even natural gas. Okay? Now, try to draw a similarity between these conditions and what I just covered in pyrolysis. It is pretty much the same, or even flash pyrolysis. Okay. Why? Through the ages, I have these mountains and the magmas coming through, through volcanic eruptions. Okay. These have transformed the series of vegetations which are growing there, and eventually all these things went down through the geological eras and get transformed into what we call these kind of products. Now, as I was mentioning in the last class, so this is a big challenge, because now all these things has happened over centuries, and now we want to emulate that in a short span of time, which is the real crux of the challenge. So, this is the basic fundamental of pyrolysis, what I wanted you people to understand. So, we will follow up on pyrolysis after this about how the pyrolysis process leads to formation of liquid fuels, gaseous fuel, and what are the challenges and what are the efficiency rate with which we challenge. But the take home message is that visualize the pyrolysis process in a laboratory condition the way I explained you, and try to visualize how the pyrolysis must have taken place through centuries underneath the earth crust, where in high pressure, high temperature and lack of oxygen, many things have got transformed into the product which we are enjoying today. So, in the next class we will follow up on pyrolysis and we will move on to the other gasification, liquefaction technique. Thank you.